I find all of this quite fascinating. Thank you for accepting this seminar. And a great title for, by the way, is Unfolding the Time Structure for Quantum Chromodynamics in Heavy Ion Collider. Without further ado, please give welcome to Liliana.
Thank you so much. Thank you very much, and thank you very much for the introduction, for you to attending, and I would also like to thank very much for this opportunity to present a colloquium here at the department. And what I would like to show you today is basically, let me just see is basically to, instead of giving you a technical seminar about this topic, instead I would like to tell you more of a story, how this story came to be. And what I would like to tell you is basically a story that starts to presenting what we think we understand about jets, about QCD jets. No, it's fine, it's fine. Okay. What we think we understand about jets. Move afterwards to what breaks our understanding of jets in the presence of a heavy ion collision, and finally show you how the key understanding of what is time in these objects reshapes the way we think about these objects. Now, before going into the story, let me just briefly present to you. Elodie already did, but in any case, you probably know me as a professor here at this department, but I'm mainly theoretical particle physics that works in exactly heavy ions. As Elodie said, I am currently the leader of the phonology group, which I helped found, and the idea of this group actually was to build a bridge between theorists and experimentalists so that we could focus more on the understanding and interpretation of data. Now the group has evolved since its inception, and now it builds more or less around 30 researchers, that most of them work in theoretical particle physics in heavy ions, but now we extend also to precision physics and beyond standard model. Under my direct supervision, more or less, I have about 1/3 of these people. That includes postdocs, PhD students, master students, etc., that produced work that I will cite accordingly. So as you can see, all these people contributed to this project in a very meaningful way. So let's step back and present you first the framework where we work. And we work on the theory of the strong interactions, quantum chromodynamics, or QCD for short. And so the building blocks that we are interested in describing are basically quarks and gluons. And even though these are the building blocks of our theory, we can never actually observe them, because this theory has a property that we call confinement. And so the only objects that we can access are not the degrees of the theory, are not the degrees of the freedom of the theory that we work with, are actually hadrons, mesons, baryons, etc., that we know that are made of these elementary particles. Now, for you to gain a little bit of understanding of how this theory is so much different of a counterpart that probably more of you are familiar with, which is the quantum electrodynamics, the very simple difference relies on the fact that photons, even though they kind of carry the electric charge from one place to the other, they are charged. They don't have any kind of charge, right? So they are neutral particles. So this means that if I have a room full of photons, they are oblivion to each other. However, gluons instead, they actually carry the color charge. So not only they are responsible for propagating information from one place to the other, they also act as additional sources of radiation. And this changes qualitatively the picture. And funnily enough, this richness actually is the one that contributes to the overall mass of the universe. The Higgs mechanism is responsible for attributing the mass to the elementary particles, but it's the QCD dynamics that generates this mass in our visible universe. So we cannot observe quarks and gluons, and instead we need to rely on these objects that we call jets. And this brings me to the first part of my story, which is a very successful one, which is the story of describing jets in vacuum. What are jets? Well, jets from the theoretical perspective are just a collection of emissions, or diagrams if you want, that are composed by basically quarks and gluons that radiate a sequence of processes, a sequence of emissions. Well, on the experimental side, we don't see this, right? We only see the final state observables, the final state particles. And so jets are basically what we use to build a proxy between what we measure and what we know how to calculate. Jets are simply just a cluster of final state particles that were originated from the initial quark or gluon. And the idea is to basically collect all the momentum and all the energy that the initial quark originated and give rise to these final state particles that we observed. So we build kind of a sequence of emissions, and we build a story out of my final state particles. That's why you can perceive these jet clustering tools. Now, this structure by itself, when we look to the theoretical interpretation of it, this structure is not random. In fact, the emissions that are how we understand these emission patterns inside of the jet, again from the theory perspective, is just a sequence of emissions that are ordered in angle in such a way that the first emissions are the widest angles, and the smallest ones are and the later ones, let's say, are the shortest angles or the smallest angles. And so the idea is, if we have some sort of structure on the theoretical side, can we build something on the experimental side to make a one-to-one comparison? And the answer is yes, we can. So in the same way that we attribute kind of a story for the theory side, we can do actually the same on the experimental side. We use these clustering algorithms to provide us a story of how this process, how this jet came to be. And as long as we find a recipe that provides us a story that is also ordered in angle, in fact, we can make a correspondence between one and the other. And so the idea is, well, now that I have two stories that are more or less similar in angle, can I make a direct connection? Can I access the QCD splitting function, which is the elementary process of radiation of QCD, despite the fact that I don't see quarks on gluons? And the answer is yes, we can. This is made by a procedure that is called soft drop. I'm not going into the technical details, but this process basically allows us to select this clustering step and mirror to exactly this elementary radiation that you see on this side. And this allows us basically to connect what we measure experimentally with what we can calculate with the theory of the strong interactions. And this has been done and provides a very successful description between what we calculate in the colored bands and what we see. So this means that jet substructure can actually reconstruct QCD dynamics with the caveat that we don't see quarks and gluons. We are just able to reconstruct the kinematics of the products of the mesons and baryons that the quarks and gluons themselves generate. Okay? But in any case, once we calculate this, we can predict the results. And in fact, not only on jet substructure, but even in the jet production itself, QCD has proven to be an extremely precise theory. We can predict about 12 orders of magnitude in the jet spectrum. So QCD is really one of the most precise theories that we have. This is probably one of the, well, not the top one for sure, but it's one big achievement for such a theory that comprises such richness and such complexity with respect to other sectors of the standard model. Now, we understand quite well jets in vacuum. But this is assuming that the jet lives in isolation, which is not always the case. So let me present you now how this story changes when we go to a heavy ion collision. When we go to heavy ion collision, we need to think how QCD matter organize themselves. Because of the gluon self-interactions, which comes from the fact that the gluon has color, in fact, the QCD phase diagram resembles something of, for instance, water. So you are familiar with water, QCD, with the water phase diagram, right? The same substance, you have liquid, vapor, solids, and despite the fact that these are the same substance, which is water, the properties of this substance is quite different between the phases, right? Sound propagation, for instance, is not the same in gas as in ice, for instance. And so the same happens on the QCD matter side. And the state that I'm more interested in studying is exactly the quark Gluon plasma that is reached when we have temperatures or the equivalent of pressures that are of extreme conditions. Okay? Now, the quark Gluon plasma was actually proposed 2 years shortly after QCD was born as a theory. Okay? But of course, it took a lot of years to reach the technology that would allow us to recreate exactly these conditions of temperatures and densities. However, we made it, so there are now relativistic heavy ion colliders that can reach these temperatures. And the way this kind of study is made is that we need to attain, for instance, heavy ions, because these allow us to basically build up density and accelerate them and collide them to extreme energies to build up temperature, so that we can basically jump from our normal matter to this corner of the phase space. And once we do that, we give the necessary conditions to form this quark Gluon plasma phase for very short instances of times, of course, because once this is formed, don't forget, due to confinement, these quarks and gluons need to hadronize. So what will happen is that this will expand, it will cool down, it will hadronize, and eventually reach the detectors. So we cannot see the quark Gluon plasma, but we can see the results of its production. Now let's look at jets. What happens to jets? Okay, we already understood quite well what is a jet in a vacuum. The problem is now when we have a quark Gluon plasma. And now we have a colored medium. So it's quite different of having my jets evolving in isolation, because now I have a color field to which quarks and gluons can interact. And this interaction, of course, will induce further radiation, because now I give a color potential for further radiation to occur. And this means that I have all the additional complication of the theoretical description of what is a jet evolution in the presence of a medium. And this is quite challenging. And so over the years, we have been, of course, made several discoveries. And what I would like to tell you is about 2 questions that are being answered by some of your colleagues. One of them, as I showed you, there is a structure in this multiple radiation of QCD in vacuum. There is an angular ordering that basically tells us how this radiation builds up to form a jet. And the way we see this kind of emissions is kind of almost like independent emissions, as long as we have this constraint on the angular space. But now in the presence of a medium, this question is not so trivial to be answered, because now we have all the complication that we have a quark Gluon plasma surrounding our particles. And so one of the questions that one of your colleagues from here, Tomas, is trying to answer is exactly if there is a factorization in the medium, or more accurately, what is the level of precision that we can achieve once we assume factorization, because don't forget, QCD is a precise theory. Okay? So we just need to know how to answer this question to provide the answer how much precise is our understanding in the case of a quark Gluon plasma case. The other thing that we need to understand is exactly how we picture now the jets in the presence of a heavy ion. This is being done by a colleague of yours that is doing the PhD with me, but it's in Granada University. And the way we understand now jets in the presence of a medium is quite different, because what we discovered is that the medium doesn't see jets the same way. That is to say, not all jets are equal to the medium. And in principle, or what we know, is that jets that have large angle emissions are more suppressed with respect to jets that have smaller angle emissions. So this is the ratio of lead-lead results, or simulations in this case, over proton-proton, and this is the emission angle of the very first soft drop splitting that I basically explained to you. And so this means that the medium resolves the jet differently and will reshape our jets also in a different way. All this is much more complicated, though, because the way we picture jets. We basically started this field by looking to the jets in the same way as in vacuum. And in vacuum, jets, or I thought it was my the way we picture jets in vacuum is actually, or the way we think of Parton showers, are just mathematical objects. They are simply constructs. They don't have any kind of physical realization, because again, we cannot see quarks and gluons. And so all this process is completely unobserved. That's what we call virtual particles. But in the presence of a heavy ions, things change. We have now a physical medium, that is the quark gluon plasma, that is expanding over time. And this expansion now provides kind of a clock. And the radiation that is emitted at this place, for instance, will experience a quark gluon plasma that is different of this one. So this means that in the presence of a quark gluon plasma, we need to rethink the way we see jets. We can no longer see them as just virtual objects in a space that lives in energy momentum. We need to consider the extra dimension that now comes from the quark gluon plasma itself. So the time expansion of the quark gluon plasma. And that is a new question that I started to pursue. And this gives rise exactly to a way at which I start to think about jets. And that's when I started to build this project, which I called ChronoQCD, and see jets as space-time objects. Now, where is the timescale in QCD? We don't have it, right? It's a quantum field theory. It's developed in energy momentum. However, we have, in fact, a timescale that is given by uncertainty arguments. And this is what we call the Parton formation time. So let's grab this formation time as an estimate. And now let's look at my Parton shower. We already know that it's ordered in angle. And we already know that by using jet substructure tools that we can retrieve its kinematic variables. And because this formation time is connected to these kinematic variables, I can also assign a formation time now to the splittings. So I can withdraw the kinematics, I can withdraw the angle, and I can withdraw the formation time. And I can basically build a kinematic phase space of this radiation. And I put here as a transverse momentum the angle, and this is the arrow that is built out of the formation time. And so I start to basically deconstruct my jet history. The first emission has a given angle, the second emission will have a smaller angle, and so on, right? And that's how I fill in this QCD kinematic phase. Now, vacuum tells us that the order in which we fill this diagram, or this phase space, is completely arbitrary. It doesn't carry any kind of physical meaning. So this means that provided two kind of paths in this, let's say, triangle that we call the Lund plane, they are perfectly equivalent. They will yield the same jet. And in fact, that's the case. What we did afterwards, and this is one of the main results of André, the PhD student that is about to finish the PhD this year, what we discovered is that when we introduce now a medium evolution here, you can see that just these two examples will not exactly experience the same kind of medium, right? Because in this case, for the yellow trajectory, the first emission and the second emission are within the boundaries of the quark-gluon plasma existence. But if I use this blue evolution, only the first emission is actually affected by the quark-gluon plasma. And so with this kind of naive setup, we made the question of, okay, let's just mimetize the effects of the quark-gluon plasma, which is mostly energy loss, okay? And let's count the number of jets that survive the medium lifetime. And what we found is that, as you can see, the number of jets that survive the medium lifetime heavily depends on the characteristics of my parton shower evolution. And this provides us the first evidence that QCD parton showers do manifest as space-time processes in the presence of a heavy ion. This, of course, in vacuum is not, we don't see differences, but when we include medium, we start to see differences. So, as a following step, okay, so if I have a formation time, maybe that's the best order for me to actually apply to jet substructure. We thought that, okay, if we are in vacuum, radiation in vacuum follows an angular ordering, so let's take this angular ordering to reshape the structure of my jet. But from this moment, why angle? Why not formation time? Because it's a time scale that maybe is connected to the quark-gluon plasma existence. And what we found, so we basically did some tests. We ran Z boson plus jet events because the Z boson doesn't carry any color charge, so it will not basically lose any kind of energy in the presence of a quark-gluon plasma, so it's a very clean sample. And we compared the energy of the jet with respect to the Z boson, because that's more or less the initial energy of my jet at the beginning of the collision. And this is basically the typical result of this kind of distributions. If we compare to experimental data, that's mostly what we see. And values smaller than 1 hint to the degree of energy loss. And afterwards, we decided to, okay, then let's split. Let's look for the 50% of my jets that have the formation time the most earliest possible. And we got that result. And when we select jets that have a very large formation time, we got that one. So formation time seems to really be separating the time scale. Or, for other words, it seems to be connected to the time that the jet spent within the quark-gluon plasma. And another colleague of yours, that is João, is now making a follow-up study exactly on this topic during its Peak 1 work. And so we started to connect the dots and see what comes out of this. And for me to answer this, let me go back again to one important caveat that I disregard, or it's implicit, that is the introduction of an additional scale. In QCD, we only care about the scale of the particles that are generating my jets. However, in the presence of a quark-gluon plasma, we have an additional scale that is the resolution scale of the medium. And this is something that we need to take account also in our theoretical results. And so the question becomes a little bit more complicated, because imagine that I have a gluon that is now separating into two. I can ask what is the resolution of this antenna, and the resolution of this, what we call antenna in QCD, which is just two particles that are connected somehow. In this case, it's the gluon-gluon, but you can think of a QQ-bar pair coming out of a photon, for instance, or even from a gluon. And this is given by the transverse, basically the transverse distance. And I call this my dipole size. And now, if I compare this transverse size with the transverse resolution of the medium, I can have basically two possibilities. One, that the medium has a transverse resolution that is larger or the order of the transverse distance between these two. So I have my dipole. You can think of a very small or very linear two particles, and I'm interacting with the bulk of matter, but the matter basically is not able to resolve each particle independently. It resolves the particle as a whole. And from that moment onward, it doesn't destroy the jet substructure. right? It isn't able to see the two particles. It sees basically a coherent state. So in this case, what we discovered is that the jet remains what we call vacuum-like. That is to say, it lost some energy, but the medium doesn't reshape its structure. Now, of course, that if the transversal resolution is smaller, then the things change. Because now I have a dipole that is very large, and basically the medium can interact with the two particles independently. And this means that it will break any kind of quantum interferences that were happening between these two particles. So my jet is somehow destroyed with respect to my vacuum expectations. So what we learn is that the medium resolution requires a sufficiently large jet substructure, sufficiently large in the sense that we need to compare with the medium itself. Now, of course, that the point is not really how the jet sees the medium, is when the jet sees the medium, or starts to see the medium, because jet substructure is not something that is static, right? Don't forget, I have a formation time that tells me what is the quantum time that is needed for two particles to behave as two new independent ones. And so, even that if a pair is created with a transverse resolution that is not enough for the medium to resolve, after some time, of course, the pair continues to travel, and at some point, yes, the medium will start to resolve this object. And so, as you can see, there are a couple of now two timescales in my actually process. So there is the formation time, which is the time at which the two particles start to behave as two independent particles. And there is what we call a decoherence time, which is the time at which the medium starts to see the two objects. And these do not need to be exactly the same. And so this means that the medium will start to probe the jets as it will evolve in time. And to test our theory, what we did was, okay, let's operate in two limiting cases to simplify things. Now this works. Okay. And one of the cases is, okay, let's assume that the formation time is always larger than this decoherence time. This means that my jet will always follow this coherent pattern, and it will behave as a vacuum-like structure. And let's operate also in the other case in which the formation time is always smaller than the decoherence time. So this means that I will assume that my medium is always able to resolve the two physical particles. So independent radiation is triggered. And now let's look to the formation time. And what we see is again the same jet, but different scenarios. And again, formation time seems what exactly controls how the medium resolves the jet. So if the medium resolves the jet, the effect of radiation is triggered, and the formation time will appear naturally with shorter values with respect to our baseline. If we take this idea even further, this is really important if we go now for smaller systems that are not, for instance, lead-lead collisions. Regarding the quark-gluon plasma presence, we know that in lead-lead, it's totally established that we have the formation of this quark-gluon plasma. But we don't know yet which conditions exactly trigger its formation. For instance, in proton lead, we have experimental results that seem to hint that perhaps there is a quark-gluon plasma there, but other observations seem to tell us no, there is no quark-gluon plasma. So it's a very still unknown physics case that we are currently pursuing. And one of the things that I'm doing also with a colleague of yours, in this case in Coimbra, is exactly understand how formation time can help us to tell when the QGP-like effects starts to switch on. And the idea is exactly to use smaller systems and use the formation time to understand if we can select jets that have produced in a very short droplet, because perhaps our question of experimental results of not seeing energy loss in these systems is just a fact of precision. Perhaps it's so small that is diluted over all jets. Now, alluding to this effort, of course, to try to understand how this might produce some significant results, we need to understand which kind of small systems to look. what are the ones that will maximize exactly our searches? And as theory convener of the LHC Physics Center, we are right now exactly with this effort to try to understand what kind of small systems, what kind of ion species we want to run during the next run 4 of the LHC. So this is kind of 2030 for you to take a memory. And so because of this is exactly extremely timely. Personally for me, of course, not as a representative of the theory community, but of course as a representative of the theory community, I'm interested in actually understanding what is the physics case of exploiting these kind of new probes. And this is something that I'm also exploiting with a colleague of yours now in Rome University, that is basically trying to understand what is the gain that we get with objects, with the observables, that are somehow related or can be cross-checked with these tests of deformation time that Manuel is pursuing, and using kind of new probes that me and collaborators have proposed some years ago, that is to use probes that are produced delayed within the quark gluon plasma. And this is the decay, for instance, we propose the TOPS, because the TOPS decays into W bosons that again are color neutral. They don't interact with the quark gluon plasma, and once this QQ bar pair is produced, then they start to see the quark gluon plasma. And of course, we can control the decay of these particles by measuring the transfer momentum. Okay? Now we thought, okay, let's go even dilutes. Don't take heavy ions at all. Let's look to proton-proton collisions, where formation time doesn't carry really a meaning. Or so we thought. This was the work done by Nuno, another of my PhD students. And one of the things that we looked at was exactly hadronization, which is one of the least understood aspects of QCT. We don't know how confinement works. We cannot describe it. And because of that, there are basically 2 classes of models that are in the market. One which is the Lund string model, and the other which is the cluster model. And we start to look by charge correlations. Why charge? Because if I have a QQ bar pair, the moment in this Lund string model is easier to explain. The moment I break this string, this QQ bar pair will need to preserve charge here along this line. And so if I now continue to basically to shower my particles, what will happen is that the charge of this quark is naturally correlated to the charge of this quark. So basically each one of these quarks will produce a meson, let's say, and statistically they will need to be correlated because I need to have charge conservation. That's what the Lund model predicts. The cluster model takes a completely opposite direction. That is to say, no, hadronization cannot be a global thing. It has to be local. Quarks and gluons move freely. They don't have constraints, and at the end, they will hadronize by trying to minimize the energy and the momentum that is needed for them to confine in color neutral particles. So this means that in this model, the hadronization is a very local property of the theory. And what we did was, okay, let's try to look for these correlations in terms of the formation time. And I might say these models are fine-tuned, of course, to data. So they will predict naturally the same kind of particle productions, the same kind of kinematic distributions, in addition to some smearings. And what we found was that actually formation time allows us to discriminate this very heavily between these 2. So we have a leverage to understand more about hadronization. And it seems that formation time, even though it's kind of root estimate, it clearly says that there is some sort of unification of the physics that we have in vacuum and what they have in the medium. And so with this, I think that more or less the boundaries and the foundations of this project are more or less built. Now, it's necessary to build the house. And despite the fact that we have found many observables, many ways to look to the problem, it's still not enough, right? We need to really understand where is our missing piece. We know that time clearly makes a role, but we want to understand more. We can create other observables that can be cross-checked with what we have so far. And one of the possibilities was actually to look for these energy-energy correlators. This is an observable that was proposed by John Ellis in 1979. Okay, so these are very old observables. But recently they gained a more significant look because they were basically observables that have a very nice connection to conformal theories, and recently also applied to heavy ion environment. Okay? For those of you that had already quantum field theory, just know that these energy-energy correlator observables are related basically to the inclusive cross-sections that you are used to deal with a quantum field theory calculation. So there is a one-to-one correspondence here. And so our goal right now is exactly to separate the emissions based on time. And the question we are making ourselves is if this observable is able to separate emissions that happen inside of the medium with the ones that happen outside of the medium. So can I build or can I tweak this observable to say what is the final, from the final distribution of particles, the ones that correspond to emissions resolved by the medium in terms of formation time, or unresolved by the medium in terms of formation time arguments as well. So we are already able to achieve, of course, this definition theoretically at what we call leading order for one gluon. For multiple emissions, it's not so trivial because we need to preserve of course, the good properties of this observable. That is to say, it continues to be an observable that is reliable, calculable at all the orders in QCT, because don't forget, QCT is a precise theory. And at the end, we need to compare exactly this experimental result, the theoretical predictions, to experiments, without relying on any kind of intermediate player here. And so this is still an ongoing process, but our preliminary results indicate that this is possible. Of course, that the next step is that these energy-energy correlators are still correlations in angle, in distance. This is not what we want. We want this observable to be directly formulated in time. And this will be Lara's master project. Finally, time is something that it's not easy to handle in quantum field theory. It's not there. However, let's look for a vacuum jet. And the vacuum jet is just an isolated system. It has its internal structure, and even in the presence of a medium, we already know that some of this structure is preserved. Then we have an environment. And an environment, it's what we call the quark Gluon Plasma, that provides an external background, and is the background to which my jet is interacting. And out of these interactions that exchange energy and color, it will inevitably induce loss of coherence and this is exactly what makes jet evolution now an explicit time dependent. So I have all the ingredients to picture jets not as wave functions as we are used to deal in quantum field theory, but actually as open quantum systems. So let's try to see how jets can be depicted. And this is exactly what we are now pursuing at LEAP with one of my postdocs that just arrived. And it's exactly to try to check how the time evolution of a jet can be built in this kind of framework. And here, of course, we now need to take into account that we have the matrix elements of my whole quantum system, or in this case, the reduced density matrix, because we trace over the medium information that we don't want to. We have, of course, the jet evolution piece, and the important part will be here. This is kind of the dissipator function that contains all the medium effects of the medium, that includes the coherence, energy loss, etc., etc., etc. And suddenly, we have an evolution equation that now has our time by free. And so, with this framework, we can now have an explicit time dependence of the jet evolution in the presence of medium. And so, my summary, jets have long been regarded as objects in energy momentum, and we are now learning that they also carry information about time. Perhaps not in the way we are used to think, but there's definitely something there. And this makes that there is a shift on perspective, otherwise we cannot understand this. So we need to, instead of regarding this process as completely virtual, we need to regard this process as being a physical consequences of something. Instead of looking at in terms of kinematics, we need to look also with an additional definition or with an additional dependence on space and time. And heavy ion collisions may actually be the first place where we can make this QCD radiation explicit, physical, measurable. So for the first time, we don't simply calculate QCD emissions. We see them evolving. As long as we have something that is evolves in time, we can see them. Thank you.